Hello. So today we will learn a very important concept that is about isomorphisms. Let us just recall what we did in the previous days. If you have to show that x is isomorphic to y, what do we have to do? The first thing, you will see that this process of showing that x is isomorphic to y, or in fact any two groups are isomorphic to each other, uh, it involves four steps. The first step is defining a function from x to y. The second step that you need to do is proving this function f that you have defined to be a homomorphism. The third thing that you need to do is you have to show that f is 1, 1. And number 4, f is onto. So some of you who are new to this field of abstract algebra, you may think that okay, this is really an easy task, okay, because we know how to prove that it is a homomorphism. We also know how to prove that it is 1, 1. We also know how to prove that it is onto. Okay, but the second, third, and fourth step, they are not usually that difficult. It is actually the first step. The first step in defining directly a function from x to y, that is difficult because you have so many functions that you can think of. But you have to think of a particular function that satisfies all the four conditions. So the first step is very tricky for most of you. In fact, for most of us. So that is why what we will do today is instead of defining this function directly from x to y, we will think of another way. We will still have to define functions, but it will be much more simpler. This next theorem in particular, it works for quotient groups. You will see. And this is a fundamental theorem of group homomorphism. You have so many fundamental theorems. You have fundamental theorem of arithmetic, fundamental theorem of algebra, fundamental theorem of calculus. This one, what we will do today is the fundamental theorem of group homomorphism. So it states like this: if f is a function from a group G to a group G dash, and if f is onto, and if it is a homomorphism, and the kernel is K, then G by K is isomorphic to G dash. So in other words, just like it's written, every homomorphic image of a group G is isomorphic to a quotient group of G. Because if f is onto, this is the homomorphic image. Homomorphic image of a group, that is homomorphic image of G, it is G dash. So homomorphic of image of a group G, that is G dash, and G by K, it is a quotient group. Isomorphic to a quotient group. What we will do today is we will prove this theorem. So let's see what we are given. We are given f from G to G dash. It is onto. It is a homomorphism. We will show that G by K is isomorphic to G dash. So if we have to prove that G by K is isomorphic to G dash, because we don't have any particular theorems, we will have to do what we have discussed. We will define a function from G by K to G dash, and it will have to be a homomorphism, it will have to be 1, 1, it will have to be onto as well. So let's see. We will define, so this is the start of the proof. Define We can denote it with f, but f has already been used over here. So I will just use another letter for this, another alphabet, that is, I will use this Greek alphabet phi. Define phi from g by k to, we need to show that g by k isomorphic to g dash, so we have to define a function from g by k to g dash. How will we define it? Define as, this is the first step, phi. How does an element of g by k looks like? An element of g by k, it looks like k g. Some of you may not remember this, but remember, all elements of the quotient group g by n, all elements of the quotient group g by n are of the form x, where x is equal to nx. Remember? So it will be a coset. So all elements has this form nx if it is g by n. But over here we are dealing with g by k, so that's why it will be kg. Alright, so I hope that is clear. Now where will we make this element land up in? We need to make this element land up in g dash. So what I will write over here equal to, this element that I will write over here, it should be sure that it will be an element of g dash, and it should somehow depend on this kg. I cannot just write g dash over here because this is too arbitrary. We don't even know what g dash is. So what will I do? This is a bit tricky. Again, just like I said, this goes in line to what I said previously, that defining this function, it is the most challenging part of this proof. The other things, homomorphism 1, 1 on 2, it follows naturally. So let's see. We have this group g by k. We have this group g dash, and this is the function phi. But we also have this function f from g, right? So we have taken an element over here, kg. Kg is this element in g by k. Now this small g comes from this group g. Because it comes from the group g, so it can also be here. Now this function already exists because it is given. So g is taken by f to g dash. An element over here will have the form fg. Because this function is already given, it already exists, it already existed, so that is why g over here will be taken by the function f to this fg in g dash. So what can we do over here? We will define a function phi from g by k to g dash in this way, fg. We are guaranteed that this element fg is in g dash. When defining the function, first of all, you have to do this part, which is well defined. Phi is well defined. We have to show it. What do you mean by phi is well defined? It means like this, because phi, it has to be a function. Even though we are writing like this, it doesn't mean that it is a function, but we still need that evidence. So firstly, for any kg belongs to g by k, we have fg belongs to g dash. That is clear because from that diagram over here. Next, what do we need to do in well-defined is we have to be guaranteed that a single element will go to a single element. Remember when you were doing functions, if A is a set, B is a set, suppose you have 3 elements, you have 4 elements, this cannot be a function. It is not a function because this element is going to two elements. This cannot happen. Even if it goes to three elements, it cannot be a function if it goes to more than one element. So that is what we will do over here. So the process that follows, if we have to prove that one element goes to a single element, it is actually the reverse of 1, 1. 1, 1, what you were doing, fa equal fb, sorry, if you have to do 1, 1 for phi, you will have to start with phi a equal phi b. You will have to get a equal b. But over here we are doing the reverse of 1, 1, so we'll start with this. We will try to get phi a equal phi b. So now let us do that. Next, but over here instead of a, we are taking elements from g by k. So what will I write over here? If ka equal kb, we will need to get that phi ka equal phi kb. Some of you may remember, because k, it is the kernel, right? K, it is a normal subgroup, so we can even write this one as ak equal bk. It doesn't matter. So what we will get over here from this line, by using the theorem on cosets that we have done during the revision, you will get ab inverse belongs to k. But k, it is the kernel k. So I can write kernel f. If AB inverse belongs to kernel f, it means that FAB inverse equal to E dash. FAB power minus 1, that is AB inverse, equal to E dash. So FAB inverse, and because F, it is a homomorphism, we can write it as FB inverse equal E dash. The reason is, since F is a homomorphism. Alright, so again we will use a property of a homomorphism. We can take the inverse outside, so you will have FB whole thing inverse equal E dash. Now from this stage, I can just easily write down, multiply both sides by FB, you will have FA FB. Multiply both sides by FB, you will have this. But FA, it's equal to phi Ka, phi Kb. How do I know this? It is because of the way that we have defined the function. Phi Kg equal Fg. So phi Ka will also be equal to Fa, and phi Kb will also be equal to Fb. So phi is well defined. So once you have this stage, you can immediately say that phi is well defined. Now we need to show that phi is a homomorphism. The second stage is phi is a homomorphism. This one you already know how to do it. Let Ka, Kb belongs to G by K. We will find on the left hand side phi Ka, Kb. This one you can write it down as phi Kab. The reason for this is, since K, it is the kernel F, kernel is a normal subgroup. It is a normal subgroup, so we can write it down like this. So phi Kg is equal to Fg, so phi Kab will also be equal to Fab. Actually, we can write this one down as Fa Fb, because F is a homomorphism. So Fa is equal to Ka fb is equal to kb, sorry, fa is phi ka, I'm sorry, phi kb. So it's equal to the right hand side. So that is why phi is a homomorphism. Next, what we will do is proving that phi is 1, 1. This is the third stage. This third stage is actually the reverse of stage 1, okay, because stage 1, just as I said, we were doing the reverse of 1, 1. So most of the times, this will be the reverse of 1. But I will just write it down anyways. Let phi ka equal phi kb. So you will have fa equal fb. If you go back in the reverse, so you will have this fa fb inverse equal to e dash. You can actually have this one as well. So if you actually go in the reverse, you will have something like this. We have done up to this stage. If you go in the reverse of 1, you will have this fa times fb inverse equal e dash, following from this. Because f is a homomorphism, you can take this inverse back inside. So again, you have split it, now recombine them back. Since f is a homomorphism, you can do that. So how do we get this stage? This element is sent to the identity, so this element will belong to the kernel. Any element that is sent to the identity will be in the kernel. It is sent by f, right? It is sent by the function f to the identity, so that's why it will be kernel f. If it is sent by some other function phi or g or whatever, then it will be kernel of that function. But over here, because it is sent by f, it will belong to kernel f. So kernel f, it was denoted by k, so therefore we have ka equal kb. So we have done 1, 1. The last part is onto. F is phi is onto. We have to prove this. For onto, we have to start with the with an element in the second set of phi when defining phi. So this is the second set, right? The second set was g dash. We have to start with an element of g dash. We will have to find a pre-image of g dash. So this is how we will do it. Let g dash belongs to g dash. What do we have to do? Have to find kg belongs to g by k, so that phi kg equal g dash. We have to find, or we have to show that kg exists. So what will we do? We have not used that f is on 2, so this is when we will use it. Since f is on 2, since f from g to g dash is on 2, if it is on 2, and because g dash is an element of this big g dash, so g dash, it has a pre-image under f because it is on 2. That is, there exists g belongs to g, so that fg equal to g dash. Always remember that if a function is onto, every element that you take from g dash will have a pre-image. But fg is equal to g dash, that is phi kg equal g dash. So this proves that it is onto. We have managed to find that there exists an element kg, so that phi kg is equal to g dash, hence phi is onto. So we have managed to prove that phi is a function that is a homomorphism 1, 1 and on 2. Therefore, phi is an isomorphism. And if it is a homomorphism, we can immediately conclude that G by K is isomorphic to G dash. Because phi is a function from G by K to G dash, and because phi is a homomorphism, therefore G by K is isomorphic to G dash. So why are we doing this theorem? Actually, this theorem is very helpful later on when we have to prove that two groups are isomorphic to each other, especially when dealing with quotient groups. So this is the consequence. The consequence of that fundamental theorem of homomorphism. If you have to show that, this is a consequence. If you have to show that x by y is isomorphic to z when dealing with groups, remember usually you used to do it in 4 stages, right? But now because we have this theorem, we can actually do it in a simpler way by using the theorem. So the first stage is we will define a function f from x to z. Alright, we will have to do this. We will no longer define directly from x by y to z. What we will do is define a function f from x to z. The second stage, the second one that we will do is we will show that f is a homomorphism. The third thing that we will need to do is we will show that f is on 2. And the fourth thing that we need to do is we will show that kernel f is equal to kernel f is equal to y. So if you manage to do all this, that is, if you manage to define a function f from x to z, if you can show that it is a homomorphism, if you can show that it is on 2, and if you can show that kernel f equal to y, then you can conclude by fundamental theorem of group homomorphism x by the kernel, that is y, is isomorphic to z. So now we have two ways how to show that two groups are isomorphic, especially when the first set is a quotient group. I think that is enough today.